Section 5.5 is the final section in this unit, and in this section we will be looking at collisions in 2 dimensions, called glancing collisions. Remember that in life, not all objects hit each other straight on or in a straight line. Sometimes objects can glance each other and hit each other at an angle. It's important to know that when we're handling these problems, that we examine things in terms of their components. So we're going to be looking at the components of momentum. The change in momentum for each component can be expressed independently. So we can look at the change in momentum in the x direction and then the change in momentum in the y direction. Similarly, the conservation of momentum can be expressed in terms of horizontal and vertical components, as shown in these 2 equations. So we have the conservation of momentum in the x direction and the conservation of momentum in the y direction. Let's start right away by looking at a sample problem. Sample problem number 1, analysis of a glancing collision. In a game of curling, a collision occurs between 2 stones of equal mass. The object stone is initially at rest, and that is the stone here in green that you can see. The object stone is initially at rest. After the collision, the stone that is thrown, which is this blue stone here, has a speed of 0.56 meters per second, and we're looking at this, in some direction represented by the angle theta. The object stone acquires a velocity of v2, 0.42 meters per second, at an angle of, and instead of theta, I want to use the Greek symbol phi. And phi is 30 degrees. You can see phi is this angle indicated right here, from the original direction of the motion of the thrown stone. Our job is to determine the initial velocity of the thrown stone. In order to do so, we're going to apply the law of conservation of momentum. I want to establish a direction convention as well. Showing in which direction we're considering positive. So we're going to look at the law of conservation momentum. We're going to look at it separately. So we're going to separate the x and y direction. Let's first take a look as to what is happening in the y direction. Be mindful of space when you're filling out these answers. I'll try to guide you so that we can conserve space and fit this all on our page neatly. If you look at the initial object, M1, this guy right here, we can see that it has a horizontal velocity or velocity in the x direction, that there is no y component to its velocity. And we know, therefore, that its initial momentum in the y direction must equal 0. If that's the case, then what must also be true is that the final momentum in the y direction must also be 0 after the collision. So, if you take a look at the resulting velocities, and hence the resulting final momentums, of these two curling stones, you'll see that for mass number 1, the velocity of mass number 1 in the y direction, its final velocity, is going upwards or north. If we add this to the component of momentum in the y direction for the second object, in the y direction final, these two should add up to 0, because we know that the final momentum in the y direction must equal 0. So we're going to start to use this information to start solving this problem. These curling stones have the same mass. So we can say that M1 and M2 are equal to each other. So we can factor this out, and we have M1 final plus V2y final, and this is equal to 0. So just as a reminder, so you know what we did here, we know that M1 and M2 are the same. And we will change this to M. Okay, let's divide both sides by M. So that we can start solving this equation. And we know now that final velocity in the y direction of object number 1 plus final velocity in the y direction for object 2 is equal to 0. Now, the final velocity in the y direction can be written as a component of the initial velocity, or the original velocity. So that would be v1y sine theta, and that's for mass number 1. For mass number 2, its velocity is in the opposite direction. So just to be clear, the velocity for mass number 1 in the y direction will be pointing upwards like this, and for object number 2, it'd be pointing downward like this. Since they're in opposite directions, we write this as v2y sine theta equals 0. And we can solve this for the angle of the initial y velocity for mass number 1. Oh, and one thing I want to be clear on is that for this guy we're using the symbol phi. P-H-I pronounced phi. Okay? So we can rearrange this and solve for theta. Sine theta is equal to V2 y sine phi divided by v1 y. We have all of these values. We know that v2y is 0.42 meters per second, and phi is 30 degrees. Dividing this by the initial y component of mass number 1's velocity, which we know is 0.56 meters per second. So sine theta is equal to 0.42 times sine 30 divided by 0.56. We can solve for theta. Theta, therefore, is equal to the inverse sine of 0.42 meters per second times the sine of 30 divided by 0.56 meters per second. And we punch this into our calculator and we get 22 degrees for theta. Let's take a look at our diagram and see what we've just determined. We've determined that this angle here is 22 degrees. Okay, now let's take a look in the x direction. We know that the total momentum in the x direction, the total initial momentum in the x direction is equal to the total final momentum in the x direction. So the only object that's moving initially is mass number 1. So mass 1, velocity 1, initial x is equal to mass number 1 is velocity final in the x direction plus mass number 2's velocity 2 in the final x direction. Good. The masses are all the same. We know that m1 and m2 are all the same. So all of these masses will cancel out, and we are left with initial velocity of mass number 1 in the x direction is equal to final velocity of mass number 1 in the x direction plus final velocity of mass number 2 in the x direction. Perfect. If we take a look, I'm going to clean up this diagram a little bit. I just want to show you exactly what we're looking at. We are looking at the x component of the velocity and the x component of the velocity. These components are the adjacent with respect to the angle and the hypotenuse. So we can write these using the trigonometric ratios. 0.56 cos, and we've just determined this angle, 22 degrees. That was the first step, plus 0.42 cos, 30 degrees. If we punch this in, we determine that our initial x component of our velocity is 0.88 meters per second. Since there is only a horizontal component, this is the total initial velocity for object number 1, which is moving to the right. So we know that the initial velocity for object number 1 is 0.88 meters per second right. Perfect. Let's take a look at an inelastic glancing collision. So, the two objects will be stuck together in this perfectly inelastic collision. It also makes solving these problems a little bit easier, so I always appreciate these types of examples. We have a skier traveling north. It's this guy right here, with an initial speed of 5.1 meters per second. And then we have another skier traveling east with an initial speed of 5.1 meters per second. They both have the same initial speed. They collide and end up in this direction. It's their final direction, VF, at some sort of angle. And we're going to use the conservation of momentum to solve this problem. So let's start examining. We know that the total initial momentum is equal to the total final momentum. The momentum of object number 1 is equal to mass 1 times the initial velocity for this object. We can sub and solve. 84 kilograms, that's mass number 1, times a speed of 5.1 meters per second in the east direction. If we punch this into our calculator, we get a momentum for object number 1 of 428 kilograms times meters per second east. I'm going to keep an extra digit, and I'm going to calculate the momentum of mass number 2. Mass number 2, 72 kilograms, and the velocity is the same magnitude, but this time moving north. If you punch this in, we get 367 kilograms times meters per second in the north direction. Very good. The momentum of mass number 1 plus the momentum of mass number 2 will equal the total momentum, the total final momentum, because these two objects will stick together. We're going to find this using Pythagorean theorem. So, the final momentum is equal to the square root of P1 squared, which is 428 kilograms times meters per second squared, plus 367 kilograms times meters per second, all squared. Solve this, and you get the final momentum of 564 kilograms times meters per second. And now we need the angle theta. Theta is equal to the inverse tan of opposite over adjacent. That's 367 divided by 428. Punch this into our calculator, and theta is equal to 41 degrees. So we can say our momentum is 41 degrees north of east. So this is our total final momentum of these two skiers stuck together, traveling in that direction. Now we want to use this to find the velocity, the final velocity of these skiers. We know that the final velocity is equal to m1 plus m2 times the final velocity. So we can solve for final velocity. 564 kilograms times meters per second, 41 degrees north of east, divided by m1 plus m2, which is 84 kilograms plus 72 kilograms. Punch this in, and we end up with 3.6 meters per second, 41 degrees north of east. Note, the textbook has solved this and reported the answer as 49 degrees east of north. They found the complementary angle instead. Both are correct. Know that they are both correct. So this is the last section in this unit. I've assigned practice problems on page 252 and review questions on page 253. I'd also like you to take a look at the self-quiz questions, the unit review questions, and the chapter 5 review questions as well.